Hello friends, welcome to this YouTube channel. Today we are going to solve a pair of numerical problems on gross efficiency and developed torque of a three-phase induction motor for a particular value of slip using its per phase approximate equivalent circuit when values of circuit parameters are given. A 400 volt, 50 Hz, 4-pole 3-phase star-connected induction motor has per phase stator impedance Z1 equals to 0.07 plus J times 0.3 ohm and per phase standstill rotor impedance referred to stator side Z2S dash equals to 0.08 plus J times 0.3 ohm. The per phase magnetizing reactance is 10 ohm and resistance representing core loss is 50 ohm. The slip is 4%. Using approximate equivalent circuit, we have to determine rotor speed, stator current and its power factor, developed torque and gross efficiency of the motor. Let us first write down the given data. Line to line terminal voltage VL equals to 400 volts. For star connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 400 divided by root 3, that gives us 230.94 volt. Given stator impedance per phase Z1 equals to R1 plus Jx1 equals to 0.07 plus J times 0.3 ohm and standstill rotor impedance per phase referred to stator side Z2S dash equals to R2 dash plus Jx2S dash equals to 0.08 plus J times 0.3 ohm. For any value of slip S, expression for rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus Jx2S dash. Given slip S equals to 4%, that is equal to 0.04 per unit. Therefore, Z2 dash equals to 0.08 by 0.04 plus J times 0.3 ohm. That gives us 2 plus J times 0.3 ohm. Now we shall calculate equivalent impedance per phase referred to stator side. ZEQ equals to Z1 plus Z2 dash. Using values we get 2.07 plus J times 0.6 ohm. This may be written in polar form as 2.1552 ohm at an angle 16.1645 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 230.94 at an angle 0 degree divided by 2.1552 at an angle 16.1645 degree. That gives us 107.1548 ampere at an angle minus 16.1645 degree. Let us now calculate working component of no load current per phase. IW equals to ET divided by RC. Given per phase resistance representing core loss RC equals to 50 ohm. Therefore, IW equals to 230.94 divided by 50, that is equal to 4.6188 ampere. Magnetizing component of no load current per phase IM equals to ET divided by XM. Given Per phase magnetizing reactance Xm equals to 10 ohm. Therefore, Im equals to 230.94 divided by 10, that is equal to 23.094 ampere. Expression for no load current per phase I0 equals to IW minus J times Im, that is equal to 4.6188 minus J times 23.094 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 107.1548 ampere at an angle minus 16.1645 degree. This may be written in Cartesian form as 102.9186 minus J times 29.8315 ampere. Applying Kirchhoff's current law, at node P we get stator current per phase I1 equals to I0 plus I2 dash. Using values we get 107.5374 minus J times 52.9255 ampere. This may be written in polar form as 119.856 ampere at an angle minus 26.2 degree. In polar form, we can write stator current per phase I1 equals to I1 at an angle minus phi 1 equals to 119.856 ampere at an angle minus 26.2 degree. For star-connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 26.2 degree, that is equal to 0.897 lagging. For three-phase induction motor, total input power Pin equals to √3 times VL into I1 cos phi 1. Using values we get √3 into 400 into 119.856 into 0.897, that is equal to 74,485.7 watt. Now we shall calculate equivalent load resistance. RL dash equals to R2 dash into 1 upon S minus 1. Given slip S equals to 0.04 per unit. Per phase rotor resistance referred to stator side R2 dash equals to 0.08 ohm. Therefore, RL dash equals to 0.08 into 1 upon 0.04 minus 1, that is equal to 1.92 ohm. Now we shall determine total mechanical power developed. Pm equals to 3 times I2 dash square into RL dash. We have computed rotor current per phase referred to stator side I2 dash equals to 107.1548 ampere. Therefore, Pm equals to 3 into 107.1548 square into 1.92, that is equal to 66,137.2 watt. Given number of poles of the motor P equals to 4 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 4, that gives us 1500 revolutions per minute. Now we shall calculate rotor speed. Nr equals to 1 minus S times Ns. Given slip S equals to 0.04 per unit. Therefore, Nr equals to 1 minus 0.04 into 1500 that gives us 1440 revolutions per minute. Now we shall determine gross efficiency of the motor. Eta G equals to Pm divided by P in. We have obtained total input power P in equals to 74,485.7 watt and total mechanical power developed Pm equals to 66,137.2 watt. Using values we get eta G equals to 66,137.2 divided by 74,485.7, that gives us 0.8879 per unit or 88.79%. Now we shall calculate developed torque. Td equals to Pm divided by 2 pi into Nr by 6T. Using values we get 66,137.2 divided by 2 pi into 1440 by 6T, which is approximately equal to 438.6 Newton meter. A three-phase 1500 kilowatts, 2300 volts, 50 Hz, 4-pole star-connected induction motor has following per phase parameters referred to stator side. R1 equals to 0.02 ohm, R2 dash equals to 0.12 ohm, X1 equals to X2S dash equals to 0.32 ohm, RC equals to 451.2 ohm and XM equals to 50 ohm. When the motor operates at a slip of 0.03746 per unit, using approximate equivalent circuit, we have to determine input line current and its power factor, gross power output, gross torque and gross efficiency. Let us first write down the given data. For stator winding, resistance per phase R1 equals to 0.02 ohm and leakage reactance per phase X1 equals to 0.32 ohm. Expression for stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.02 plus J times 0.32 ohm. For rotor winding, given resistance per phase referred to stator side R2 dash equals to 0.12 ohm and standstill leakage reactance per phase X2S dash equals to 0.32 ohm. For any value of slip S, expression for rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 0.03746 per unit, therefore Z2 dash equals to 0.12 by 0.03746 plus J times 0.32 ohm. That gives us 3.2034 plus J times 0.32 ohm. Let us now calculate equivalent impedance per phase referred to stator side. ZEQ equals to Z1 plus Z2 dash. Using values we get 3.2234 plus J times 0.64 ohm. This may be written in polar form as 3.2863 ohm at an angle 11.23 degree. Given line-to-line terminal voltage VL equals to 2300 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 2300 divided by root 3, that gives us 1328 volts. We have determined equivalent impedance per phase ZEQ equals to 3.2863 ohm at an angle 11.23 degree. Expression for rotor current per phase referred to stator side I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 1328 at an angle 0 degree divided by 3.2863 at an angle 11.23 degree. That gives us 404.1 ampere at an angle minus 11.23 degree. For three-phase induction motor, expression for total air gap power PG equals to 3 times I2 dash square into R2 dash by S. Given slip S equals to 0.03746 per unit and per phase rotor resistance referred to stator side R2 dash equals to 0.12 ohm. Therefore, PG equals to 3 into 404.1 square into 0.12 by 0.03746, that is equal to 15,69,323.3 watt. Expression for total gross power output PM equals to 1 minus S times PG. Using values, we get 1 minus 0.03746 into 15,69,323.3. That gives us 15,10,536.4 watt. Let us now calculate working component of no load current per phase. IW equals to ET divided by RC. Given per phase resistance representing core losses, RC equals to 451.2 ohm. Therefore, IW equals to 1328 divided by 451.2, that is equal to 2.94326 ampere. Magnetizing component of no load current per phase IM equals to ET divided by XM. Given per phase magnetizing reactance XM equals to 50 ohm. Therefore, IM equals to 1328 divided by 50, that is equal to 26.56 ampere. Expression for no load current per phase I0 equals to IW minus J times IM, that is equal to 2.94326 minus J times 26.56 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 404.1 ampere at an angle minus 11.23 degree. This may be written in Cartesian form as 396.36283 minus J times 78.69765 ampere. Applying Kirchhoff's current law at node P, we get input current per phase I1 equals to I0 plus I2 dash. Using values, we get 399.30609 minus J times 105.25765 ampere. This may be written in polar form as 413 ampere at an angle minus 14.6 7673 degree. Let us now calculate stator core loss. PSI equals to 3 times ET square by RC or VL square by RC. Using values we get 2300 square divided by 451.2, which is approximately equal to 11,724.3 watt. Expression for stator copper loss, PS copper equals to 3 times I1 square into R1. Given per phase stator resistance R1 equals to 0.02 ohm. We have determined input current per phase I1 equals to 413 ampere. Therefore, PS copper equals to 3 into 413 square into 0.02, which is approximately equal to 10,234 watts. Now we shall determine total stator losses. PS equals to PSI plus PS copper. Using values we get 11,724.3 plus 10,234. That gives us 21,958.3 watt. Let us now determine total power input. Pin equals to PG plus PS. We have obtained total air gap power PG equals to 15,69,323.3 watt. Therefore, Pin equals to 15,69,323.3 plus 21,958.3. That gives us 15,91,281.6 watt. Given number of poles of the machine P equals to 4 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 4, that is equal to 1500 revolutions per minute. Expression for gross efficiency of the motor eta G equals to PM divided by P in. We have obtained total gross power output. PM equals to 15,10,536.4 watt and total power input Pin equals to 15,91,281.6 watt. Therefore, eta G equals to 15,10,536.4 divided by 15,91,281.6. That is equal to 0.9493 per unit or 94.93%. Expression for gross torque TD equals to PG divided by 2 pi into Ns by 6T. We have obtained total air gap power PG equals to 15,69,323.3 watt. Therefore, TD equals to 15,69,323.3 divided by 2 pi into 1500 by 6T, which is approximately equal to 9,990.6 Newton meter. We have determined input current per phase I1 equals to I1 at an angle minus phi 1 equals to 413 ampere at an angle minus 14.7673 degree. For star-connected induction motor, input current per phase equals to input line current. Let us now calculate input power factor. Cos phi 1 equals to cos of 14.7673 degree, that is equal to 0.967 lagging. So today we have solved a pair of numerical problems on three-phase induction motors. By solving these problems, we have learned how to determine cross efficiency and develop torque of a three-phase induction motor for a particular value of slip using its per-phase approximate equivalent circuit when values of circuit parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.